Swayam Prabha. Digital India. Educated India.
Good morning, everybody. Today, our topic is conduction in a semi-infinite solid. We will consider a semi-infinite solid, which means that dimension of this solid body in Z, Y, and X, all three directions extend to infinity. Z direction we can see that extends to infinity, Y direction extends to infinity, X direction extends to infinity. Now suddenly at t equal to 0, that is at and at phase x equal to 0, we raise the temperature to T infinity. Otherwise, this semi-infinite solid was initially at a temperature T naught. So everywhere temperature was T0, time instant. At phase x equal to 0, the temperature is raised to T infinity. So that high temperature will penetrate in the x direction, and we require to find the penetration depth of this temperature perturbation or this temperature. Now the governing equation is obviously given by del temperature del T, del uppercase T by del lowercase t, del temperature by del time equal to alpha del 2T del x2. The initial condition, as I have said, that in this solid body, the initial condition is uniform temperature everywhere. That is T equal to T0 or T naught at time T equal to 0. Temperature is T naught at time T equal to 0. T naught is a temperature everywhere. And at x equal to 0, we raise the temperature to T infinity. And what we want to see temperature distribution, but we know one condition, that is for finite time, after the time elapses, the temperature is expected to penetrate in x direction. But if x direction dimension again becomes infinity, that means x direction becomes very long, so there the temperature will remain at the initial temperature. So this is the physical problem which we will solve. Now here we prefer to go for similarity transformation. I will explain what it is. We are saying theta is basically excess temperature over T infinity. Theta is given by T minus T infinity. As such, T infinity is a high temperature which has been prescribed at x equal to 0, which has been applied to x equal to 0. So T minus T infinity, and theta is function of x, it is penetrating in x direction with time t, and alpha thermal diffusivity is the property. Now instead of keeping theta as a function of x and t both, we formulate a parameter eta and make theta dependent on eta, and eta has x and t both, and obviously thermal diffusivity is a property of the solid, so that is also included. So now if we find out alpha del 2 theta del x2, we have just since eta equal to x by root over 4 alpha t, instead of writing del x, we can write basically 1 by 2 alpha t into del eta. So here we have written that twice. That means we have written del 2 del x2 operated over theta. So alpha, this is del x2 operated over theta, and instead of del x2 we have written this parameter 1 by 2 root alpha t del t, 1 by 2 root alpha t del t, del eta. Sorry, del eta. So basically we can see this will become alpha divided by 4 alpha t and del 2 theta del eta 2. Del 2 theta del eta 2. So this is basically alpha del 2 theta del x2. Then del eta, del t of theta, sorry, del theta del t, we can write as del theta del eta into del eta by del t. Del theta del t, this we are writing as del theta del eta into del eta del t. This is basically del eta del t. So we are changing the variables of the equation. That means instead of keeping it del temperature del time equal to alpha del 2t del x2, we are changing the independent variable as eta. So we can write now 1 by 4t del 2 theta del eta 2 plus x divided by 4 root over alpha t into t del theta del t. Simply here we have substituted basically del 2 theta del x2, and here we have substituted del theta del t, or del theta del eta effectively. So we can now write this form del 2 theta del eta 2 plus twice eta. If we multiply it by 4t, this t and this 4 will get cancelled out, x by root alpha t, and that is nothing but twice eta. So twice eta d theta d eta. Now we substitute phi equal to d theta d eta. So this second order equation we can write as a first order equation. So del phi del eta plus twice eta into phi equal to 0. So we can write d phi by phi equal to minus twice eta d eta. So it is simple operation, d phi by d eta plus twice eta phi equal to 0. From here d phi by phi equal to minus twice eta d eta. And if we perform the integration, ln phi equal to minus 2 eta square by 2 plus C1. And then we can write this as ln phi equal to, this is same, minus eta square plus ln A. Instead of C1, we are writing basically ln A. So we can write ln phi by A equal to minus eta square, which gives us phi equal to a to the A e to the power minus eta square. And our original substitution was phi equal to del theta del eta. So that means del theta del eta equal to A into e to the power minus eta square. Now if we integrate d theta between eta equal to 0 to any eta, we can write eta equal to 0 to any eta, a e to the power minus eta square d eta. So we can write from here this integration theta at eta, and this will also have minus theta at eta equal to 0. We are transferring that to the right hand side. So basically theta at eta equal to integration 0 to eta to the power minus eta square d eta plus theta at eta equal to 0. So we can write theta equal to a 0 to eta, integration 0 to eta e to the power minus eta square d eta. And we know eta equal to x divided by 4 root over alpha t. So if x tends to infinity, we can see if x tends to infinity, theta will be theta 0, because theta is defined by t minus t infinity, and t is t naught at x equal to infinity. In other words, at eta, when eta tends to infinity, theta is theta naught or t naught minus t infinity. So applying these two boundary conditions, we can write theta is basically t0 minus t infinity, a 0 to infinity e to the power minus eta square d eta. Now this integration 0 to infinity e to the power minus eta square d eta, we can quickly look at it. 0 to infinity e to the power minus eta square d eta. If we substitute minus e to the power minus eta square by e to the power minus z, that means eta square by z, then we can write d eta equal to dz divided by twice z to the power half, which can be written as half 0 to integration 0 to infinity e to the power minus z into z to the power half minus 1 dz. This is basically half gamma half into gamma half. Gamma half is root pi. So this is root pi by 2. Now a into 0 to infinity e to the power minus eta square d eta. This integration is a root over pi by 2. Basically it is a gamma function, gamma half by 2. So root pi by 2, we can write this. So from here we can write a equal to 2 into t naught minus t infinity by root pi. So then a is found out. We can write theta equal to 2 by root pi t naught minus t infinity into integration 0 to eta e to the power minus eta square d eta. So we get the complete expression for theta. And from here, again, theta is t minus t infinity, that is on the left hand side. Right hand side also we get t0 minus t infinity, t naught minus t infinity. So from there we can write t minus t infinity divided by t naught minus t infinity equal to, then just rearranging this. This is t minus t infinity, left hand side. From right hand side, t0 minus t infinity, we transfer to the left hand side denominator, and we get t minus t infinity divided by t0 minus t infinity equal to 2 by root pi 0 to eta e to the power minus eta square d eta. Remaining terms, 2 by root pi integration 0 to eta e to the power minus eta square d eta. Now this is basically known as error function. So we can write t minus t infinity divided by t0 minus t infinity is error function of eta. And what is eta? Eta is x by x divided by root over 4 alpha t. So this is t minus t infinity divided by t0 minus t infinity. So x divided by root over 4 alpha t is error function, and we can calculate the values of error function. We can see, we vary it from 0 to 0.2, 0.4, 0.02, 0.04, 0.06, 0.1, 0.12, this way up to 1.8. I have not written all the values of the argument of error function after 0.16. It will be 0.18, 0.2, etc. It will take it up to, we'll calculate it up to 1.8. And then we'll get the values. We can see for 0.02 it is 0.02256, 0.04 it is 0.04511. This way at 0.16 it is 0.17901, and 1.8 it is 0.98909, close to 1. So we again define theta bar, which is 1 minus basically t minus t infinity divided by t0 minus t infinity. So 1 minus t infinity divided by t0 minus t infinity, which is theta bar. We get t0 minus t divided by t0 minus t infinity. Rearranging, we can write t minus t0 divided by t infinity minus t naught. And this is theta bar, and theta bar is also nothing but we have subtracted this quantity, basically t minus t infinity, t0 minus t infinity from 1 to get basically this t minus t0 divided by t infinity minus t0, and that means we have subtracted error function x with argument x by root over 4 alpha t from 1. So this is plot of theta bar, which is 1 minus error function. So at x equal to 0 it is 1, and at 1.8 it falls down to 0. So theta bar equal to 1 at eta equal to 0, and theta bar equal to close to 0, 0.01 at eta equal to 1.8. Thus, at eta equal to 1.8, the body temperature is at initial temperature. And why we are calling it body temperature? Because this is T minus T naught divided by T infinity minus T naught. Original body was at T naught temperature. At the x equal to 0 location, temperature was raised to T infinity. So this was the total difference, and this is at any x location at any given time, the temperature is T. So basically here we can see that theta bar or this temperature reaches almost T naught, so that this theta bar becomes close to 0. So this is basically that penetration is indicated by eta value of 1.8. So at x equal to 1.8, root over 4 alpha t, theta bar is close to 0 and t equal to T naught. We can say that temperature perturbation at the surface has penetrated to x equal to 1.8 root over 4 alpha t, and this depth is called the penetration depth. Penetration depth increases as the square root of time t. Quite clear. The solid with high thermal diffusivity means thermal diffusivity we know K divided by rho Cp. That means high conductivity and low heat capacity. That means conduction dominated over storage. So more heat is conducted inwards. Increased penetration depth is obtained for high thermal diffusivity. Reverse is true for low thermal diffusivity. Now, since we got T minus T infinity divided by T0 minus T infinity, that was our final solution, 2 by root pi integration 0 to eta e to the power minus eta squared d eta, where eta is given by x divided by root over 4 alpha t. So from here we can find out del t del x, which will be obviously T0 minus T infinity into del x of 2 by root pi 0 to eta e to the power minus eta squared d eta. And we can substitute f as, we can substitute this quantity 2 by root eta 0 to eta e to the power minus eta squared d eta by f. Then we can write df dx equal to df d eta into d eta dx, and we can write this quantity. So finally we can write df dx equal to 2 by root pi e to the power minus eta square by root over 4 alpha t, or e to the power minus eta square divided by root over pi alpha t. It is then del x is basically we can write del t del x, we can write del t del f into del f del x, and del t del x. So finally we can write T0 minus T infinity, basically T0 minus T infinity, and here df dx we get as e to the power minus eta square divided by root over 4 pi alpha t. So e to the power minus x square by 4 alpha t, that means which is minus eta square divided by root over pi alpha t. So heat transfer at the surface at x equal to 0 is given by Q equal to minus Ka del T del x at x equal to 0, which is nothing but Q equal to minus Ka T naught minus T infinity divided by root over pi alpha t. So this is heat transfer, and then also we can see it is a function of time. So this is basically the expression for heat transfer. Now just we will define the homogeneous and mathematically homogeneous and non-homogeneous problems. The problem will be referred to as a homogeneous problem when both the differential equation and the boundary conditions are homogeneous. So that means for a homogeneous problem, we can write del 2 t del x2 plus del 2t del y2. That means basically Laplacian t equal to 1 by alpha del temperature del time. So this is unsteady state heat conduction equation in the region R for t greater than 0. K del r del theta del ri, r is the spatial dimension, k del t del ri plus ht equal to 0 on boundary which is encompassing the region R for time t greater than 0, and t equal to fr, that is spatial function in the region R for t equal to 0. So this is in the region R for t greater than 0. This is at the boundary for t greater than 0, and this is in the region R for t equal to 0. We can call all such problems as homogeneous problem where the differential equation and the boundary conditions are homogeneous. Non-homogeneous problem we have also defined, which is Laplacian t plus grt by k equal to 1 by alpha del temperature del time in the region R for t greater than 0. This is another source term, and then k del t del ri, spatial variable, plus ht into frt on the boundary S for time t greater than 0, and t equal to fr in the region R for t equal to 0. For t equal to 0, it is fr, but t greater than 0, we can see in the governing equation and also on the boundary, we find the functions which are grt and frt, which do not include t as product. So here the differential equation and the boundary conditions are non-homogeneous. Also, we would like to just mention about the error function, since we have used error function here. So error function x is given by 2 by root pi integration 0 to x e to the power minus t square dt. T is a dummy variable here. The error function is an odd function, so that error function of minus x is minus error function x. In addition, error function 0 is 0 and error function infinity is 1. The complementary error function with argument x is defined as error function c complementary ERFC x is argument is 1 minus again error function x. So this is basically 1 minus 1 by 1 minus 2 by root pi integration x to infinity e to the power minus t square dt. We have not used a complementary error function in this problem, but we may come across in our, in other problems. So just since we are mentioning about error function, we are also, we took this opportunity to mention about complementary error function. Thank you very much for your interest. Thank you.